So any doubts what we have covered till date?
सर फ्लूइड मैकेनिक्स का कोर्स क्या है एमएससी तक का?
क्या कह रहे हो?
सर फ्लूइड मैकेनिक्स का कोर्स क्या है सर? एमएसटी में कहाँ तक आ रहा है?
एमएसटी में जो आपका वो था, क्या बोलते हैं, मोस्ट प्रॉब्ली जो कॉन्टिन्यूटी या बर्नौलीज इक्वेशन तक होगा मैक्सिमम, लेकिन आपका थोड़ा सा कम कवर हुआ था तो आपको वो देख के फिर कॉमन जो मिनिमम होगा वही होगा, जो आपका ग्रुप का और जो दूसरा ग्रुप है, जो मिनिमम उस कॉमन मिनिमम होगा वही होगा आपका एमएसटी का।
डेरिवेशंस होंगे सर?
ओके सर।
Derivations as such I cannot say anything, मतलब जो भी कवर हुआ है it will be based on that, whether it is derivation, whether it is numerical, whether it is a conceptual question. So the thing is you need to understand the basics, need not bother about what is the pattern of the question, because once you know the basics you can attempt any question. So please keep that in spirit, don't go by कि कितने मार्क्स का क्या आना है, I will prepare that, because that is what you have done till +2, and in your engineering as well as in your professional life this kind of approach does not work at all. You need to understand the underlying concepts and you should be in a position to apply those. Should we start?
Yes sir.
Okay, then I am starting with the discussion regarding conservation of linear momentum. So till now you have covered, I think, conservation of mass. So in conservation of mass you saw that conservation of mass when applied to any of the flow models, which were the 4 flow models, Ayush?
यस सर।
Which were the 4 flow models?
सर फ्लो मॉडल्स सर कंट्रोल वॉल्यूम मतलब क्या बताना है, मतलब फ्लो मॉडल?
Fixed, finite size control volume, fixed in space.
अच्छा ये वाला ठीक है सर। फाइनाइट साइज और एक सर मूवेबल कंट्रोल वॉल्यूम और एक डिफॉर्मेबल कंट्रोल वॉल्यूम।
Moving in space. Then third was differentially small control volume,
डिफॉर्मेबल
fixed in space, and deformable, differentially small control volume, moving in space. So out of these, which two are based on Eulerian approach? Which two are based on Eulerian approach? Which two?
Second and fourth.
First and third.
First and third. So first and third are based on Eulerian approach because you have fixed the region in space in which you will analyze as the fluid goes through that. And second and fourth, they represent the Lagrangian. So this should be clear. And we have actually derived this expression, that is the Reynolds transport theorem, which was a connection between Lagrangian and Eulerian approach, connecting what? Finite size control volume. So this was a theorem which connected the finite size control volume from Lagrangian to Eulerian or Eulerian to Lagrangian back. So these were the two formats of the same equation. The only difference was that in case of stationary and non-deforming control volume, we had this expression, and this expression in this case could further be simplified as curly n by curly t control volume. Whereas in case of moving and deforming, we cannot make such kind of conversion for this term as we did in the first case. and secondly, this V was replaced by V relative. So that was the essential difference between the two.
Excuse me, sir.
Han.
Sir, can you zoom out the screen a little bit? It is too much zoomed in.
So I should zoom it out.
Yes, sir. थोड़ा सा zoom out कर दो, sir.
So now let me know, is it okay?
Sir, वो pixelate हो चुका है काफी. Sir, yes.
Okay, I
better.
got it. The problem is actually the equation itself has got little bit of deformation.
Okay.
Wait for a
Okay.
second. There is no other reason for that. So that is not the issue with the screen size. That is the issue with the inherent equation written here.
All right, sir. All right.
So this is the Reynolds transport theorem. And if you remember, when we were applying conservation of mass, what was capital N written as? What was capital N? For conservation of mass?
Small m.
Small m. What was the small n equal to?
1.
1. So now we will be taking this concept forward with the only difference that now this n does not represent mass, but it represents the linear momentum. So that is the only difference, and that's why it is so easy now. We can actually find out conservation of linear momentum by simply putting n is equal to, what should I put n equal to?
Small m.
In case of conservation of linear momentum.
Small p.
Sir, mv, sir, m into v.
M into V. What is small n equal to?
Capital, sir, v खाली velocity.
Capital N upon small m, this is V. Clear? Any doubts to anyone? Any doubts to anyone? So by putting this, I am giving you 30 seconds. Come up with the expression. I am giving you 30 seconds. What will you do? How will you approach? So this was, I am writing down here dmv upon dt. So I have put mv instead of n. This is equal to d by dt. Here again mv. But this is now for control volume. This was for system plus double integral control surface. N is v now, rho v dot dA. Any doubts to anyone in this expression? Any doubts to anyone? Now you know that if this is non-deforming as well as stationary control volume, so what can you do with this term? What can you do with this term?
Sir, m dv by dt.
Can I replace the ordinary derivative with what? The partial derivative. So this is what I can do if I have this condition in place. That is, this ordinary derivative can then be converted to partial derivative.
वो को लिखा हुआ है आपने non deforming st.
And stationary. Non-deforming and stationary. Any doubts to anyone? So I am putting it here. It was dn. So this was dmv upon dt. This is for system. This is equal to, I am curly by curly t. This is m into v. This is for control volume plus double integral, surface integral over the control surface v rho v dot dA. Now what is m equal to? If you remember, what is m equal to? Rho into small volume triple integral. Any doubts? Any doubts? This m here can be written down as this or not? Is this clear to you? Any doubts to anyone? So I am taking the right hand side now. This term I am not considering now. So I am considering the right hand side. And what about this term? Can you convert this into a corresponding volume integral term? What should I write down here? And which theorem will convert the surface integral to a volume integral?
Stokes theorem.
Be careful, Gauss divergence theorem. So please remember, from surface to volume is
Divergence
always
theorem.
Gauss divergence. So from closed surface to volume is Gauss divergence. From surface not closed to a line integral closed is
Stroke.
Stokes
Curl.
theorem. Fundamental theorem of curls also, or Stokes theorem.
Yes.
So please remember this. And you know that what is the statement? Integral of a derivative over some region in space is equal to the value of the function at the boundaries. So that is as simple as that. Now with that statement, help me out to write down the equivalent volume integral expression for this surface integral expression. What should I write down here?
So del dot
Del
V.
dot del dot
So del dot rho V vector.
rho v vector or v rho v vector?
सर V rho V vector मतलब हाँ V rho V vector D है.
V rho v vector into
सर
small
dV
volume
dV dV.
dv. Clear है? किसी को कोई doubt? Any doubts to anyone? And what about this term? I am writing down this term as a combined term now. So this term can be written down as, what should I write down? Triple integral control volume curly rho v by curly t dv. So this becomes equal to dmv by dt system. Any doubts to anyone in this expression? So what I have done is I have simply put the value of mass in this term and converted from surface to volume integral using using Gauss divergence theorem or fundamental theorem of divergence. Any doubts to anyone? Any doubts to anyone? So this is what I have
सर
written
एक बार
down.
नीचे स्क्रॉल डाउन कर लो.
हाँ जी?
मेरा एक बार लीव हो गया था. सर मेरा लीव हो गया था एक बार, तो एक बार स्क्रॉल डाउन करके वो फॉर्मूला दिखा दो इसके ऊपर वाला.
एक सेकेंड, आप कौन सा वाला कह रहे हो? दोबारा से बोलो.
सर ये जो अभी लेटेस्ट हमने डिराइव पूरा कर रहे हैं ट्रिपल इंटीग्रल वगैरह. यस सर एक बार नोट कर.
सो ये क्लियर है आपको?
सर यहाँ पे रो V vector कैसे आया यहाँ पर? del by del t रो V vector. सर सेकंड इसमें कंट्रोल वॉल्यूम वाली में से. हाँ सही वाली हाँ यहाँ पे.
v वेक्टर तो ऑलरेडी है. m क्या था?
अच्छा ठीक है ठीक है हाँ ठीक है सर ठीक है
क्लियर है?
यस सर हाँ वो दिखा नहीं सर.
हाँ जी. अब आप बताइए कौन थे जिनको समझना. आपका क्या नेम है? हेलो. So I'm explaining in a moment. So this was the Reynolds transport theorem. This was a Lagrangian term, that is dn by dt system. This was curly n by curly t control volume plus surface integral n rho v dot dA. So in this case, in case of conservation of linear momentum, you have put n is equal to mv and small n is equal to V. By substituting these values, you get this kind of expression when you substitute these values into the Reynolds transport theorem. यहाँ तक clear है? So after you have put the values of these small capital N and small n, the next step is on the right hand side, you are making substitution for mass. Mass is rho dV. And you are making substitution or converting this surface integral to volume integral using Gauss divergence theorem. So these are the two steps which I have done to get this final expression. Are you clear, hai?
Yes, sir.
So you also know that you have volume integral here. So you could combine the two terms as well. Can you combine the two terms on the right hand side? Wait for a second. So these are the two terms. So I am combining the two. So this becomes equal to triple integral control volume curly rho V by curly T plus del dot V rho V. So everything inside and I have dV here. किसी को कोई भी doubt? Any doubts to anyone? So I've combined the two terms and that was the only motivation that I could combine these two terms if I use the Gauss divergence theorem to convert surface to volume integral. Any doubts to anyone? So you can see here I have written down in a much more neater way. So this is what you have done. I think this is now absolutely clear to you what I have done here. Any doubts to anyone? This was the control volume which was in this fluid, and this is conservation of linear momentum. So I have simply replaced n with momentum. Now this is clear to everyone, this term I've already derived. This term is clear to all, and this term is also clear to all. The term which I have not talked about is this term. So this rate of change of linear momentum of the system will be equal to what? What do you think? If there is some ball, its mass was m,
Sir,
its
it's the
force was
force.
v1. Hanji.
Force.
It
Force
will be equal to force. Hanji, clear hai? Any doubts to anyone? So if the momentum is changing of any object or fluid element in this case, then it means some force is being applied on that particular system. So this rate of change of linear momentum on the left hand side could also be written down as force. Now this force could be of two types, whether it can be a surface force or a body force. Is that clear? So any kind of force, as far as engineering mechanics is concerned, you could categorize this force into two parts, that is surface forces and body forces. So you are conversant with these two kind of forces? Are you conversant or not?
Yes, sir.
So,
Yes, sir.
so what do you mean by surface forces? It acts on the surface or through it requires a surface,
Surface contact.
whereas a body force does not require a contact, surface or a point. So if this was a table and say this was a book lying on the table, if I ask you to draw the Freeboy diagram of this book, what surface force will be acting on this book?
Normal reaction.
Normal force.
Normal reaction. So that is acting on this surface. What else will be acting on this book?
Gravitational force.
Gravitational pull.
mg.
So mg will be acting on each and every part of this book, but I could show this with a single vector at its center of
Gravity.
gravity. So this is the body force, one of the body forces. You can have other body forces also, and this is the surface force. So you will realize that in mechanics you essentially deal with these two kinds of forces. These are the two categories of the forces. Now with this background, let me know, this is the fluid control volume. What do you think? What surface forces will be acting on this control volume? What all surface forces will be acting on this control volume?
Point force, sir.
Pressure force.
Pressure force? Anything else?
Point force.
What is buoyant force? Buoyant force is pressure force only.
Yes, sir. Yes.
So we have already accounted for pressure force. I am writing down pressure force because pressure force is much more appropriate to use.
Viscous effects of fluid.
Viscous effects of fluid. So do you have any other surface forces here?
हेलो सर,
हाँ जी।
सर ये जो आपने इक्वेशन लिखी है सर, dmv अपॉन dt इक्वल्स टू वॉल्यूम इंटीग्रल और पार्शियल डेरिवेटिव ऑफ रो वी वाला टर्म जो लिखा है।
हाँ
सर जब ये रो वी वाला जब टर्म आप डिराइव कर रहे थे तो उसमें आपने लिखा था पार्शियल डेरिवेटिव ऑफ एम वी वेक्टर बाय dt बाय डेल टी।
ठीक है,
सर फिर आपने m को रिप्लेस किया था
ठीक है।
उसे वॉल्यूम इंटीग्रल से, तो
ठीक
फिर
है।
सर ये जो डिफरेंशियल जो टर्म है, ये पार्शियल डिफरेंशियल, ये कंट्रोल वॉल्यूम जो आपने लिखा है इसके बाहर नहीं आएगा?
इसके बाहर? हाँ मैं वही बोल रहा हूँ, आपने ये चीज उस दिन शायद आपने लिबनीज रूल देखा था उस दिन? Did you see the Leibniz rule? So this is the Leibniz rule, which I think explained to you earlier also, that the total derivative terms comes inside and you have the partial derivative term here. So this was the case I am showing you here. ये आपको याद है पिछली बार हमने किया था?
Yes sir.
What happens is, if you have something like this, d by dt from a to b, fx, say fx is, f is a function of x and t, then this is equal to a to b curly f by curly t xt into dx. यहाँ भी dx आना था. This is only possible when a and b are fixed. They are not function of time, as this was the case. So this is called Leibniz integral rule, that is, you can take in the derivative sign inside if the limits are not changing respect to time.
So ये हम लोग सिर्फ उसके लिए ले सकते हैं ना, कंट्रोल वॉल्यूम अगर हम लोग का स्टेशनरी है तभी यूज कर सकते हैं।
हाँ, so
मूविंग में नहीं।
ना मूविंग में नहीं, तो मूविंग में थोड़ा सा डेरिवेशन चेंज हो जाएगी, then I would not be converting this into partial derivative, then this will remain d by dt. And clear है?
Yes.
So this Reynolds transport theorem, this dn by dt could be converted to curly n by curly t only when it is stationary and non-deforming. So I am taking this simple case forward. Otherwise, I will have to do it like this only. D by dt will remain outside and then I will have to integrate it. Is that clear?
Yes.
So I could take it inside only assuming that the control volume is fixed in space. So that is the inherent assumption in this. The thing.
सर
हाँ जी बताइए.
सर ये हम मूविंग वाले केस में पार्शियल डेरिवेटिव्स में क्यों नहीं लिख सकते, एक बार बताओगे?
मूविंग वाले केस में
पार्शियल डेरिवेटिव्स के टर्म्स में क्यों नहीं आ सकता वो?
अच्छा, तो दिस इज द केस, से you are able to look at this. Wait for a second. Is this visible to you? Is this screen visible to you? This one?
Yes sir, yes sir, yes
This
sir.
integral rule. So in the previous case, we noted that A and B were fixed. That is,
Yes,
these
sir.
were not changing. This was the case.
Yes sir.
But when they are changing, what happens is, it is something like this. Say fxt was the function at some time t. After some time delta t has elapsed, that is at total time t plus delta t. This is the function where it is. So if I want to now evaluate, as I did for the previous case, what should I write down? D by dt integral a to b f x t dt, sorry dx. ये तो clear है? Again,
Yes,
I
sir.
want to evaluate this integral. Now, by using the principle of limit or the derivation, the definition of the derivative, what should I write down here? Limit delta t tends to 0. What else? What should I write down?
fx at t plus delta t
A to
minus
now
integral of
where if this is fx t plus delta t.
yes sir.
Now, what are the limits at t plus delta t? The limits themselves have changed. So that
Yes,
is
sir.
a plus dA by dt into delta t
Yes sir.
to b plus dB by dt into delta t.
Yes sir.
So this minus what? fxt from a to b dx
Yes sir.
upon everything upon delta t in the limit delta
Yes,
t
sir.
tends to 0.
Yes sir.
So this actually results in an expression which is different. So can you find it out, or because I don't want to waste time, this actually end up in this kind of expression. If I remember fxt dt, this becomes equal to, I think, a b xt, then it becomes minus f at plus f bt, and there is some term here also. So I can leave this as an exercise. आपको सिर्फ इसको open up करना है. You will end up in some different expression. So then this ordinary derivative is not equal to only the partial derivative, but there are some correction terms also when the limits are changing with respect to time as well. So that is why if the limit themselves are changing, then I will have to use this formula to convert the ordinary derivative to the equivalent partial derivative term. Are you clear? Hai? In the interest of time, I am not attempting this because this will take another 15-20 minutes if I go into details of each and every aspect. What I can tell you now is, this is the effective area that comes. So this is actually curly f by curly t into dx. This is the limit term. That limit has changed for a. This is the limit term that has changed for b. So this is the net expression for d by dt integral fxt ab. So this is this area. What you are seeing in pink area minus this red area gives you the answer of this. Likewise, I have shown it here also. This blue area minus this green area gives you this. You will get to know how. I leave this as an exercise. If time permits, we can discuss it some other day when the time is there. Is that clear?
Yes, sir.
So that is why we don't, for this case, we are simplifying the case. That is, we are converting the ordinary derivative to partial derivative only with the assumption that the control volume is stationary and it is fixed in space. These are the forces acting on this control volume. So this is the Lagrangian approach. And this is the control volume approach. So this is the relationship between the two. Now these were the surface forces. You identified surface forces as pressure force and viscous force. What about body forces? What all body forces will be acting on this control volume?
The gravitational force.
Gravitational force. Is that clear? So as such, the conservation of linear momentum involves body forces as well as surface forces. In body forces, primarily we are relating with the gravitational force, and surface forces we are relating with pressure force and the viscous force. Now, are you able to see this structure here? What is this representing? What is this representing? These arrows are representing what?
Velocity profile.
Velocity profile. This is a plate. This is the velocity profile. So where is your analysis going on? This is a control volume. This control volume has some part in which the velocity is varying and some part in which velocity is not varying. So now let me know this surface and body forces. I have told that there is a gravitational force as far as body force is concerned, and there is a viscous force and pressure force as far as surface forces are concerned. Say instead of being located here, the control volume was, say, located at this location. What will be the difference? What will be the surface forces then?
Only the pressure forces.
Only the pressure force. Is that clear? Although viscosity is non-zero everywhere. Viscosity is non-zero everywhere. So you don't have any fluid in this universe as far as it is known that has zero viscosity. You cannot have zero viscosity. Viscosity will be always not equal to zero. That is for sure. So then why are we not considering viscous force as one of the forces when the control volume chosen is outside this boundary layer? Boundary layer समझते हैं आप? A layer of fluid in which velocity variation is there, that is called the boundary layer. Above this region there is no relative velocity, although viscosity is there. So what does that mean?
Viscous effects present नहीं होंगे.
Why?
हम लोग नहीं
Viscosity is
दिखेंगे.
always there. Then why there are no viscous effects?
सर क्योंकि relative slip नहीं है ना between the different layers अभी के लिए.
Okay. So here fluid is as if it is moving as a rigid body. As if the fluid itself is a rigid body. So you can assign a single velocity to the entire control volume, as if everything is moving with the same velocity. So there is no relative. What does that mean? Viscous forces are always acting here, but they are acting equally, so that in a sense it is not experiencing any unbalanced viscous force. Here there is unbalanced viscous force. For instance, this was the body here. The bottom layer AB and the top layer CD will experience different magnitudes of the force. So there is imbalance of viscous force here. But here there is no imbalance of viscous force here. So what happens is, in effect, although viscous forces are present in both the cases, in both the regions, the effect of viscous forces is not felt here. And please remember, this is very important. This region is called inviscid region of flow. Inviscid region of flow. So please don't ever confuse. Inviscid region does not mean viscosity is zero, because viscosity can never go zero. It only means there is no imbalance of viscous forces. So net effect is balance. So you don't experience, the object does not experience any kind of, this fluid element does not experience any kind of viscous force. So that is what is called inviscid region of flow, where viscous forces can be actually neglected. So please be careful. What do I mean by inviscid? So there is no inviscid fluid. So please, this is entirely incorrect terminology. You cannot have any kind of inviscid fluid. You can only have inviscid region of flow. Are you clear? Hai? Any doubts? Now let me know. So there was an aerofoil, or there was an object. Fluid was flowing in this direction. Now let me know what will be the, I'm drawing the streamlines. Now what do you think? If this was on an object which was in the flow, which region could you consider as inviscid region of flow for this particular solid body? Is that clear? If this was some solid object, here we are not talking about solid object, here we are talking about the fluid itself. So fluid will not be obstructed by this fluid element. But if you have a solid region, say you have kept a metallic object like this, you know that fluid will flow past that object. So now my question is, I am marking here A, B, C, D. So which region you will assume that fluid is, or which inviscid region of flow? Which is the inviscid region of flow?
C and D. C and D.
So this region is inviscid region of flow. This region is inviscid region of flow. What about these regions? You cannot neglect the viscous forces here. So this is not the inviscid region of flow.
Yes.
Are you clear? Hai?
Yes.
So please be careful it is always the region of flow. You cannot talk about inviscid fluid. You will always say inviscid region of flow. Likewise, if you have, again I am showing you, this is again the layer in which fluid is changing velocity. And if you look at the fluid, this fluid will be undergoing rotation. Whereas above the boundary layer, the velocity is same and the fluid is not rotating about its own axis. So this is irrotational region of flow. And this is rotational region of flow. Any doubts? So again, you can have distinct regions. That is, in certain regions, there will be rotational effects, and in certain regions, there will be negligible rotational effects, and you can call them as irrotational regions of flow. We'll come to this in detail when we do this irrotational region of flow. But as far as today's lecture is concerned, you should always keep in mind, we only have regions of flow. We don't assign properties to the fluid itself. That is, we cannot say this is irrotational fluid. It does not mean anything. Likewise, we cannot say it is inviscid fluid. It does not make any sense. You need to identify the regions in space or in the flow field that you can call as inviscid or irrotational. Clear? Any doubts to anyone? Any doubts to anyone? So please remember, conservation of linear momentum, if I apply to inviscid region of flow, then that is given a special name called Euler equation. So Euler equation is only a special case of more generalized conservation of linear momentum. So in general, conservation of linear momentum applies to any region of flow. But when I want to derive the Euler equation, Euler essentially did it assuming the region to be inviscid region of flow. So now the analysis, as far as Euler equation is concerned, we will be always talking about inviscid region of flow. That's why I have shifted this control volume to a region in which there is no variation in velocity. Are you clear? Hai? Any doubts to anyone? So that now in this case, the surface force will only be pressure force, and you will not have any kind of viscous force. So please remember, it does not mean viscous force is zero. It only means something has balanced, but the viscous forces have themselves balanced each other. So that is what is meant by that viscous forces are negligibly small here. It does not mean that they are essentially negligibly small. It means only the net viscous force is zero, not the absolute magnitude of the viscous force. Any doubts to anyone? Any doubts to anyone? So I am reiterating this fact in a moment. Reynolds transport theorem is a method to convert from Lagrangian to Eulerian or Eulerian to Lagrangian for finite size control volumes. There are certain physical laws which we have identified: conservation of mass, momentum, energy, entropy. What happens is we apply these laws to certain models of flow. These model of flows can be finite size control volume fixed in space, finite size control volume moving in space, differentially small control volume fixed in space, differentially small control volume moving with the flow. So we have till now done it for mass. We have substituted the capital N equal to m for conservation of mass and small n equal to 1, and we got the continuity equation. Likewise, when we substitute n is equal to linear momentum and small n is equal to v, we end up in conservation of linear momentum principle. And one of the special cases of those conservation of linear momentum principle in which that principle is applied in inviscid region of flow gives us the Euler equation of motion. So please remember, Euler equation is not different from conservation of linear momentum. The only thing is it is applied to inviscid region of flow only. So I will continue with this in the next lecture. Meanwhile, go back and try to reflect on the concepts which we have developed today. Thank you. So I'm ending the lecture now.